Hi guys, and welcome to today's class. Today we are looking at statistical inference, and specifically we are talking about inference for multiple linear regression. In statistics 2, we have looked at statistical inference for the mean and also for the proportion. We have done that for single samples, so we have looked at hypothesis testing for one sample mean, for one population mean, sorry, for one population proportion, and also for independent samples. That's why we looked at the difference of population means and the difference of population proportions. So in this class, we shall be looking at statistical inference for multiple linear regression. And basically here we are talking about the inference for the regression coefficients. The regression coefficients or the regression parameters, the beta j's, which we said that they are always unknown. They are always unknown, but we use the beta j hats to estimate them. So we shall be testing hypotheses revolving around that. But before we go there, let me remind you the meaning of statistical inference. Statistical inference. So we say that statistical inference is the process of predicting, sometimes use the word estimating, the values of population parameters using sample statistics. So that's a very brief definition of what we call statistical inference. So we'll be making estimation or prediction. We'll be predicting the values of population parameters. Remember, population parameters are always unknown, and that's why we must always estimate them or we predict them using the information that we get from the samples. Okay, using information from the samples. Okay. So statistical inference entails two main things, or entails two main processes. Entails two main processes. So when we talk about inferential statistics, these are things that you should think about. Number one is estimation. And estimation comes in two ways. We have what we call the point estimation and what we call interval estimation. When we talk about point estimation, here we use a single value, a single numerical value from the sample to estimate the population parameter or the unknown population parameter. For instance, from what we have covered in statistics 2, for instance, you can use X bar is 20. These are single value as an estimate, to the mean, where this is sample mean. The sample mean is a statistic. So we can use the value that we get from the sample mean to estimate the population mean. So these are statistic, this is a parameter. So we use the statistic to estimate the parameter. That's what we call a point estimation. We use a single value. That's not a very popular way of estimation because of the uncertainties that come with the samples. Because usually we assume that the sample is random. So when you choose a subset of the population, that is a sample, then it is good to appreciate the fact that there are many other possible samples that you could have used. But here you are basing your conclusion on just one sample. So it's not a very popular way of estimation or of making inferences. But sometimes we do it. We do it for some statistics. Then the other type of estimation is interval estimation. And basically what should cross your mind here is what you call the confidence intervals. Confidence intervals. I think you've covered the calculation of confidence intervals for the mean, for the proportion, either using one sample or two independent samples. Okay, so estimation is part of the process we are calling statistical inference. Then the other part, or the other part is is hypothesis testing. Hypothesis testing. Okay. And I think you've covered a lot of this, especially you've tested hypotheses about the mean, the proportion, and so on and so forth. So we'll be doing the same. We'll be testing hypotheses, but now we'll be testing hypotheses revolving around the beta naught, beta 1, beta 2, all the way to beta k. We'll be testing hypotheses revolving around those statements. So the process that we saw of hypothesis testing is the same we shall be using here. All the 6 or 5 steps that are used in hypothesis testing, we shall be following them in this context. Okay. So next we are going to look at the sampling distribution of the OLS estimator. And the sampling distribution is something that you've come across in statistics too. I remember you were introduced to the sampling distribution of the mean. And you say that if you have a sample, let's say, and I think I've given an example using a population with 3 elements, A, B, and C, where their measurements are 1, 2, and 3. And then suppose this is your population of size capital N is equal to 3. Then you want to pick a sample of size N is equal to 2 and calculate the mean. That is the sample mean. You want to pick a sample of size N is equal to 2 from this population. And then you calculate the mean. It is good to appreciate that, or the fact that there are many different samples that you can choose from here. And we can consider, if you consider an example where you are sampling with replacement, you can have 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. So if you are sampling with replacement, you have 1, 2, 3, 4, 5, 6, 7, 8. You have 9 samples that you could choose. And from every sample, you can get a value of X bar. You can get a value of X bar. So if you can calculate the values of X bar in each case. Okay. And because in statistical inference, we assume that the samples are random, it means that you choose one of these samples, possible samples randomly. That means you assign equal chances to each and every possible sample. And we notice that the values that you put here, or the values of X bar are not constant. So this is not constant. So the values that you put here are changing from every possible sample to another. You find that the value is changing from one sample to another. That means we can look at X bar, as some variable. We can look at X bar as some variable. And just like any other variable, it means that X bar must be having a probability distribution. It means that X bar must be having a probability distribution, just like any other variable. Maybe you can have a few values here for you to appreciate what we are saying there. So you can have, so I'm calculating the mean from every possible sample. So this plus that, this would be 1.0, this would be 1.5, this will be 2.0. So these are the possible values of X bar if I were to use the given samples. So this will be 1.5. This will be 2.0, this will be 2.5, this will be 2.0, this will be 2.5, and this will be 3.0. So you notice that the possible values of X bar are actually like a variable. They are not constant. It's not a constant. And just like any other variable, we said that then X bar must be having a probability distribution. And we said that that probability distribution of X bar is what you call the sampling distribution. Sampling distribution of the mean is what we call the sampling distribution of the mean. And if you plot these values, knowing that, if you convert this table into a probability distribution, as you know, the samples are equally likely. So if you are to say probability there, this would be 1/9 for each one of them. 1/9 for each one of them, like that, all the way to here. So if you are to convert this into a nice table, maybe you will get something like that. the possible values of X bar. The first one is 1.0, 1.5, 2.0, 2.5, and then 3.0. Those are the possible values of X bar. Then you put the probability so that you end up with a probability distribution. You notice that the probability that X bar is equal to 1 is just appearing once. So this would be 1 out of 9. The probability that X bar is 1.5 is appearing twice, and each probability is 1 over 9. So this would be twice 2 out of 9. Then probability that X bar is 2.0, you'll be getting is appearing 3 times. So the probability there is 3 out of 9. Then 2.5, you'll notice it is 2 out of 9. And finally, 1 out of 9. And we say that if you plot these values, if you plot these probability values, if you call this one X bar, that's your variable, then here you have the probability. You will end up with, so if this is a 1.0, 1.5, 2.0, 2.5, and 3.0, if you are to, just sketching, if you are to plot these probability values, you will end up with something like that. You will end up with something like that. And you know, if you are to fix a smooth curve here, you will be able to guess the kind of distribution. And you notice that even from these values here, you can notice that this is a symmetrical distribution, which looks like that. It's a symmetrical distribution, which looks like that. And this is what you call a normal distribution. Normal distribution. So the shape will tell you, because you can see the mean is here. It's also the midpoint, and it's also the mode, most occurrence. So that is clearly a normal distribution. So what you're calling the sampling distribution of X bar is actually a normal distribution. Is actually a normal distribution. And when you say it's a normal distribution, then there are two things that you must mention. Number one is what is mu. Number two, what is sigma. Sometimes some people will call it sigma squared variance. Okay, so it is easy to show using this information that if you are to find the mean of these the possible values of X bar, you notice that this will be equal to 2.0. And that is the mean. This is my population, remember. So if you find the mean of these values here, the mean of those three numbers, which is mu in this case, will also be 2.0. So we're saying that now X bar, the sampling distribution of the mean, is normal with mean equal to mu. So this value here is also equal to mu. And standard deviation, let me write in words. Let me write this in words. So with mean equal to mu, and standard deviation, it is possible to show that the standard deviation will always be given by sigma over root n, where sigma is the variance from here. It's the variance from here. So in here you get the variance, which would be sigma. So the standard deviation of, sorry, this is not variance. This is variance is sigma squared. So sigma is the standard deviation. Okay. So it's good to notice that the standard deviation of these values now, the values in this column, the standard deviation of those is given by this formula. And that standard deviation is not just called a standard deviation. We call it the standard error. Standard error of the mean. Okay. So the standard error of the mean. So the sampling distribution can be explained using that illustration. So even for other statistics, and now we're in the context of regression coefficients. So even the regression coefficients, because we know they come from samples, they also have their sampling distribution. And that's what we want to discuss. We want to check whether it is going to be normal, just like we saw here, or it's going to be something else. That's what we want to look at today. All right, so if there's no question, let's proceed. Let's start by saying consider the regression model. Consider the regression model that is yi is equal to beta naught plus beta 1 x1 plus all the way to plus beta k xk plus plus the error term plus the error term. Okay. I hope you remember the classical assumptions. We listed number 1 up to number 5. So we want to add another assumption. We want to add a 6th assumption. So we say to the classical assumptions, we add this. We add this assumption. So this is our assumption number 6. Assumption 6. That, and the assumption is that the error term, which we are calling U, is independent of x1, x2, all the way to xk. In other words, the error term or the residual is independent of the explanatory variables. Is independent. That means they are not correlated. That means they are not correlated. That's why you saw we mentioned somewhere that the covariance of U and Xi's is equal to 0. The covariance is equal to the covariance of U and Xi is equal to 0. Okay, so is equal. Is independent, and the error term itself has a normal distribution with mean 0 and variance equal to that sigma of U squared. Okay, which means that U has a normal distribution. It means that U has a normal distribution with mean mu is equal to 0. I think this one we mentioned earlier on, that the mean of the error term must always be equal to 0, because we said that if you are to sum the UIs, you'll always get 0. If you sum them, if you sum the errors, you should, and we did this practically, so you get something very close to 0. So that means if you are to divide it by n, which is now gives you the mean, you'll also get 0. You'll also get 0. Okay, so with mean equal to that, and variance equal to sigma squared of U. Sigma squared. So this is variance of the residual. This is variance of the residual. Okay. Then we say now, under the assumptions 1 to 6, under the assumptions 1 to 6, conditional on the sample values, of the explanatory variables, we can say this. This statement is very important, that beta j estimate has a normal distribution with mean equal to beta j, there is no hat there, and variance equal to sigma squared of beta j hat. So that statement gives now the sampling distribution of the regression coefficients. So that is the sampling distribution of the regression coefficients. So beta j hat here, the first item here, these are the sample estimates. So we have things like a beta naught estimate, we have beta 1 estimate, beta 2 estimate, and so on and so forth, all the way to beta k estimate. So we are saying, remember, in the context of what we've just explained about X bar, we say that X bar, don't write this, X bar has a normal distribution. That's the explanation we are having up here. X bar has a normal distribution, as you can see, this normal distribution, and the mean, we can always show that the mean is equal to the mean of the population, okay, with mean equal to mu, and standard deviation equal to sigma over root n. So that's what we said about X bar. This is the sampling distribution of the mean. So on the other hand, this is now what is up there is the sampling distribution of the regression coefficients. This is the sampling distribution of regression coefficients. So the distribution of those estimates is normal, very important distribution, is normal, and the mean is equal to this is the true, this is a parameter, this is a true population parameter. And then this is the sample estimate. And then this is the standard error. No, this is a variance. If you take the square root, you get the standard error. So this is a variance of the regression coefficient of the estimated regression coefficient. If you take the square root of that, if you take the square root of sigma squared of beta hat like that, you'll get sigma. You'll get sigma of beta j. And this is what we previously called the, now what is here is what we call the standard error of the regression coefficient. The standard error of the regression coefficient. Okay. So so let's give more details. So we say that so we are continuing from here. So that is the sample estimates. This guy here, the sample estimates beta j hat have a normal distribution. With their mean being equal to the population parameter beta j. Remember, beta j is a parameter, so it's always unknown. It's the one that we're estimating, beta j, and a variance equal to sigma squared of beta j hat. Okay. So what does that mean? So that means that you see this statement here is very important. So if we know that the distribution of beta j is normal, then we can also define a standard normal distribution, which is quite easy to work with. So we are going to define the standard normal. So we're going to define beta j in terms of the standard normal distribution. So that means that if you take beta j hat minus beta j divided by the square root of sigma squared beta j hat, this one has standard normal distribution. So this is what we call standard normal distribution. So I hope you recall, I want to be giving you the analogy of the mean. I want you to recall that in the context of the mean, we have x bar minus mu divided by standard error of x bar, which is the same as x bar minus mu over sigma over root n. It is good for you to appreciate the fact that this is the same as x bar minus mu over sigma squared over n, then you have it like that. So, but when you simplify, you end up with this. This is what we commonly use. So we are having exactly the same thing, where the divisor here is the standard error. Same case here. The divisor here, the square root of sigma squared beta j, beta hat j, is the standard error. It's the standard error of the estimate of beta j here, this guy, the square root of that is the standard error of this statistic there. Okay, so which means that so we have, that means that this is true, this is standard normal. So which means that the variate beta j minus like that divided by square root of sigma squared beta j has a standard normal distribution. Has a standard normal distribution. Has a standard normal distribution. You know, the standard normal distribution has mean equal to 0, and this is variance or standard deviation. Variance equal to 1, the standard normal distribution. Okay, so basically that's what you call the, so that means later on we shall be using either a t, so later on we shall be defining either z is equal to beta j at minus beta j divided by the square root of sigma squared beta j. Okay, so this is standard normal. Okay, then you can also be defining equivalently t is equal to beta j, Victoria, I'm coming to you. So beta j minus beta j there divided by square root sigma squared beta j with some degrees of freedom. Degrees of freedom will be defined. I'll be defining them in a few minutes. Huh? So when you say, when we mention that the statistic has a standard normal distribution, that means we can end up with this. We can end up with this. And if you remember, in the case of sample mean, we are using z is equal to x bar minus mu over sigma over root n. This is when sigma is known. When sigma is known, you use that. When sigma is known, you use that. If we are sampling from a normal distribution, you use that. But if sigma is not known, you use t. If sigma is not known, you use t, and you define it like this: s over root n. And then you define the degrees of freedom. You define the degrees of freedom. So we shall be doing the same thing here. We shall be doing the same thing here. Okay. So in this case, when sigma, in the context when we're using t, you notice that here we shall be replacing this with an s. We shall be replacing this with an s because sigma squared j is a known. It's a known, you estimate it using the sample information. So Victoria, I think you have a question. So let's move to hypothesis testing for single population coefficients. And we shall be using the t-test, the t-statistic in this context. Okay. As you know, as the size of the sample increases, the t-distribution is approximately equal to the normal distribution. So we are safe. We are safe starting with the t-distribution. And again, in most of the cases, the standard error of the true population parameters will always be unknown, is always unknown. So we shall be using the calculated or the estimate of the standard error of the regression coefficients. We shall be using the estimate, that's the sample estimate. And that's why the t distribution is a good starting point. Okay, so let's say under the assumptions 1 to 6, under the assumptions 1 to 6, beta j estimate minus beta j divided by the square root of s squared beta j estimate like that. You notice that we have used s here, not sigma, because we're assuming that sigma is a known. And when sigma is a known, you do not use the z, you use the t statistic. But if the sample is large, you can use the z. You can use the z, or the t is approximately equal to the z. So this item here has a t distribution with n minus k minus 1 degrees of freedom. Okay, so let me write in words. That is beta estimate of j minus beta j divided by the standard error there, which is square root of s squared beta j has t distribution, the student's t distribution with n minus k minus 1 degrees of freedom, with n minus k minus 1 degrees of freedom. It's good for you to note that n is the size of the sample and k is the number of parameters estimated in the model. For instance, if you have beta naught plus beta 1, if you have something like that, then the number of parameters here is equal to 2. Okay, if you have a multiple case like this, plus beta 1, let's say x1, beta 2, x2. So here, the number of parameters is 3. So these are the parameters that have been estimated. So this is one estimate of parameter, another one. 1, 2, 3, and so on and so forth. So you take n minus k minus 1. Remember, in most of the, we always recommend that n should always be bigger than the number of parameters there. N should always be bigger. N should always be bigger than k. Okay. Then another note that we can make there, so let's call this one number 1. Another note that we can make there is that sigma squared of beta j of beta hat of j has been replaced by the sample counterpart. That is a squared beta of j. So we're saying that here, the divisor here, or this guy here, has replaced sigma squared of beta. If you remember what we said earlier on we said that we are supposed to be working with this. I think we mentioned here. We have replaced that. This is a population parameter. We have replaced it with the sample counterpart. Okay. And then number 3, we note that sigma squared or s squared of beta j can be simplified. So we are saying that this can be simplified to, when you take the square root, it just becomes s of beta j. So I think this is an easier way of writing it. So instead of writing s squared, then you take square root, you just write s of beta j with a hat. Okay. And sometimes it is denoted as the standard error of this estimate, beta j estimate. So that's what we are calling S of beta j. So the standard error. Okay, so this is the standard error of the regression coefficient. J. So this is a standard error of the regression coefficient beta j. Okay. So if you check the output that you'll get from Excel, if you perform regression analysis, you will notice that in the third table, we have the coefficients. Those are examples of, those are point estimates of the true parameters, which are always unknown. Then here we have the standard error. the standard error. So this is the standard error. Hope you can see. So the first value here is the standard error of beta naught estimator. And this is the standard error of beta 1 estimate and the standard error of beta 2 estimate. So we have extracted them and put them here. Okay, so these values are coming from here. Then we have the coefficients which are up here. Well, sorry, which are down here. So the standard error, when in the context of multiple linear regression, for convenience, you'll be advised to use Excel to obtain them. But if you are in the context of simple linear regression, it is easy for you to calculate them using the formulas that I mentioned to you. The formulas that are here, we covered these in the last 2 weeks. So standard error of beta 1 estimate and standard error of beta naught estimate. But in the case of multiple linear regression, you can use Excel to obtain those to save time. Okay. So now let's see, how do we define the null hypothesis? How do we define the null hypothesis? The null hypothesis. Remember, we're dealing with single population coefficients. Okay. So we say that in most cases, our interest is to test the null hypothesis that is test the null hypothesis, this one, H naught, that beta j, notice that there is no hat there, is equal to 0. In the context of hypothesis about means, we were doing this, that mu is equal to 0, for instance, or some other value here, maybe some mu constant, some mu naught. So we're having the same. So this is the population parameter in question. The same case here, this is the population parameter, which is always a known, Okay. So this is the null hypothesis that by default we are testing. So this just means that the given regression coefficient, for instance, we are talking about something like this, H naught, that beta 1 is equal to 0, for instance. That's just an example. So J can take the values 0, 1, 2, all the way to K. So if we say this, it means that we are testing the effect that the variable, the coefficient, the variable corresponding to beta 1 has no effect in explaining the dependent variable. For instance, if you have something like this, Y estimate is equal to beta naught plus beta 1 hat, like that. Let's say plus beta 2 x2. If we have something like that, if we are testing this, if we are saying we are testing whether the effect of the variable x1 is equal to 0, that means this variable here is not helping the prediction of this, or the effect is 0. So basically, that's what the null hypothesis means. We are testing whether the effect of the given variables, independent variables, is actually 0 in the effect on the dependent variable. Okay. Then we say that the calculated, in this case, the calculated T statistic, the calculated T statistic for a particular regression coefficient is given by, so you say T of beta j, T of beta j estimator is given by beta j estimate. Here there should be a 0, but because there must be always minus whatever the value is here. Remember the formula looked like this, minus beta j divided by standard error of beta j. So, but in this case, in the kind of hypothesis that we are testing here, this value here is 0. So that's why That's why the formula looks like this. So we're going to have beta j, beta with a hat, divided by the standard error of j. So you take the regression coefficient estimate. So this is the estimated regression coefficient divided by standard error of the particular regression coefficient. Standard error of the particular regression coefficient. So the test statistic T is given by this formula, which has a T distribution. So this guy here has a T distribution with n minus k minus 1 degrees of freedom. Degrees of freedom. Example, let me have some illustrations. Example, the T statistic for beta naught hat is given by T beta naught hat is equal to the estimated value of beta naught divided by standard error of beta naught hat, like that, and so on and so forth. Okay, so using a similar approach, we can define the T statistic for beta 1 estimate. So we'll have T of beta 1 is equal to the estimate of beta 1 divided by the corresponding error. So you can do that for all the regression coefficients. So every regression coefficient will have a corresponding T. So if you use Excel to do the analysis, you will find that the T statistics are obtained for you here. And by default, if you're using software, or for instance Excel, to do regression analysis, the default null hypothesis is that beta j is equal to 0. So this is the default. This is the default null hypothesis. So when you're using your software, by default, this is the hypothesis that will be tested. So the T statistic, when you're using Excel, will be obtained using this formula here. Will be obtained using that formula. So when you come to Excel here, because you've done the regression analysis, and you have the regression coefficients here, and you have the standard error, then we're saying that these values here are obtained by taking this value here divided by this. So we have extracted them here. These are the standard errors. These are the regression coefficients there. So if you want to find the T statistics, you just take the estimate, which is this value. So that is our beta naught estimate, divided by the corresponding standard error, like that. And this value here, as we saw earlier, this value is exactly equal to this value here. So this value is obtained in a similar way. So you take this is equal to, you take the regression coefficient divided by the corresponding standard error. And finally, we also do, you take this divide by the corresponding standard error. So once you have the estimates of the regression parameters and you have the standard errors, then hypothesis testing becomes quite easy, because you just need to obtain the statistic. Then you can use the statistic to obtain the p-value, and then you make your conclusion. Or you can go ahead and use the interval estimation. You can compute the confidence interval. We shall be doing this a little bit later. You can compute the confidence interval, and then you test the hypothesis that is of interest. And by default, we are testing whether the regression coefficient there is equal to 0. Again, as of course some alternative hypothesis. Okay, so so for example, we have said that we've given that example, and then we say that these T statistics are printed in standard computer output in regression, in computer output, in regression applications, So we're saying that these values are always given by default when you perform regression analysis using some software like Excel. I think we have seen that they are always there. Okay, then it is good for you to note that you can compute them. You can compute them if you are given the beta j estimate and the corresponding standard errors of beta j. If you are given these two, we have seen and we have done it. It is easy for you to obtain the standard errors. So for instance, if I give you a test, then I leave this column blank here. If I leave this column blank here, if I leave it blank, if I leave all the others blank, you should be able to complete them. I can leave the others blank like that. Then using the available information, it is possible for you to obtain the the standard errors. Of course, for you to it's possible for you to obtain the remaining. It's possible for you to complete the remaining part of that table. Okay, because you know the formula. All right, so let's have some example for illustration purposes. Yeah, so this is example. We have an extract of the output from regression analysis using Excel. So, and we're saying that by default, you'll always get the coefficients. So this is your beta naught estimate. This is your beta 1 estimate, and this is your beta 2 estimate like that. The standard errors are given here. And then we have the t statistics here, which are obtained by taking the coefficient divided by that. The coefficient divided by the standard error, like that. Okay. Then after that, now, once you have this is equivalent to the t calculated. The t calculated. Okay. So that is just about the null hypothesis. As you know, we have another type of hypothesis known as the alternative hypothesis. So let's talk about it. Hypothesis. And as you know, the alternative hypothesis has three possibilities. It can be either less than, can be greater than, or can be not equal to. But by default, and that means when you're using a software to do the analysis, by default, it will be testing a two-tailed test. So if this is our null hypothesis, that beta j is equal to 0, then by default, this is what we shall be testing. That beta naught, but that beta j different from 0. This is the default. The default. But there are other possibilities. You can have beta j is less than 0, or you can have beta j is greater than 0. Okay. So let's say that we say that the statement of the alternative hypothesis is always guided by the problem that you are solving, by the problem being solved. Okay. So then you say that the problem can suggest one of three possible scenarios. So one, it can suggest that H1, that is the denotation for alternative hypothesis. H1 is such that beta j is not equal to 0. This is the default. The default. Then we have number 2, that H1, that beta j is less than 0. Then we also have H1 such that beta j is greater than 0. So the alternative hypothesis can take any of those three ways. Okay. So if Roman 1 is your possible, is your alternative hypothesis, this calls for a two-tailed test. It calls for a two-tailed test. That means that you are going to apportion your critical region on both tails. You're going to equally apportion the critical region or the rejection region on both tails of your distribution. Okay. Then if this is your alternative hypothesis, this calls for a lower tail test. Lower tail test. Okay, so that means that you put the entire critical region on the lower tail of your distribution. Then this one is calling for an upper tail test. An upper tail test, where you apportion the entire critical region on the upper tail of the distribution. When we talk about a two-tailed distribution, if you assume either the T or the normal distribution, we're talking about this. So these are two-tailed tests. This is what you call a two-tailed test. So the shaded part here is alpha over 2, and even here is alpha over 2. This is 0. Then you can, this is two-tailed test. Two-tailed test. Then you can have a lower tail test. Assume this thing is symmetrical. Then you have alpha is there. So this is alpha. Then you can have the upper tail test, which looks like this. This is your alpha. Good to note that alpha is the level of significance. Alpha is the level of significance, which will always be given, or if it's not given, you use the default one, which you're going to measure in a few minutes. Okay, so so this is a lower tail test. Lower tail test. This is an upper tail test. Okay, so the shaded part in all the diagrams is called the critical or the rejection region. Then the unshaded part is called the acceptance region. The acceptance region. So these names are coming from what we actually do to the null hypothesis, because hypothesis testing revolves around the null hypothesis. And basically, it's about getting evidence from the sample to either reject the null hypothesis or you fail to reject, or sometimes you can say you accept the null hypothesis. Okay, but usually we use the word reject null hypothesis or fail to reject the null hypothesis. You notice that the alternative hypothesis will only help us in deciding where to put the critical region, but the hypothesis being tested is actually the null hypothesis. Is the null hypothesis. Either we reject it or we fail to reject it. Okay. Okay, so let's note the following. Number one is that the decision rule in all the cases, is to reject the null hypothesis when the calculated t statistic, when the calculated t statistics falls in the rejection region. So if your calculated value of t falls in the shaded region, what we are calling the rejection region, you reject the null hypothesis. You reject the null hypothesis. Okay. Then we also note that the rejection or the critical region is obtained using, so in this class we shall be using the critical or tabulated or the table t statistics. So you use the t distribution tables for given levels of alpha and degrees of freedom to obtain the critical value of t. So this point here is what we are calling the critical. So this is t critical, that point, even here, t critical. That value, you will get it from the tables, from the t distribution table. So if you're using the normal distribution tables from the z tables, so even here, this is your t critical. And even in the last case here, this is your t critical. So those values are read from the tables. They are read from the tables. They are not calculated. So the one that we saw from our output, the values that are here, these values here are t calculated because we calculate them using the formula that I shared with you earlier on. So these ones are the ones that we are saying they can fall either in the unshaded part or in the shaded part. So if those calculated values fall in the shaded part, you reject the null hypothesis. Okay, so if they fall in the unshaded part, you fail to reject the null hypothesis. Okay, but we shall be doing that more practically. Then our note number 3 here. So this we can call this number 1. So our note number 3 here is that the critical value of t is obtained when we know the following. When we know the following. So there are 3 things that we must know for us to be able to get the t critical, for us to know the t critical value. And the first thing that we must know is the level of significance. This is usually denoted by alpha. The level of significance denoted by alpha. Then we say that the most widely used levels of significance are most widely used levels of significance are alpha is 5%. This is what we use by default. So if you're using Excel, then this is the assumed level of significance unless you change it manually. Okay, we sometimes use alpha is 10% and alpha is 1%. So these two are also used, but they are not the default ones. And sometimes there are people who can use 0.1%, but this is rarely used. It's rarely used. So these 3 are widely used. This one is rarely used. By default, we use 5%. If you're solving a problem and the level of significance is not given, then you should use 5% all the time. Okay. Then in addition to that, so we're saying that we need to know 3 things. That's number 1. We also need to know, number 2, the type of test. The type of test. That is whether one tail or 2-tail test. You need to know whether you are doing or you are performing a 1-tail test or a 2-tail test. And this is always guided by the alternative hypothesis. So that will always be guided by the alternative hypothesis. I think we did that. So once you know the alternative hypothesis that you want to use, then that will tell you what you need to do there, as we mentioned a little bit earlier there. So that's the second thing that you need to know before you get the critical values of t. Then thirdly, you need to know the degrees of freedom. The degrees of freedom. That is df. And df is always given by n minus k minus 1, where n is the sample size, k is the number of parameters that have been estimated. You minus 1, then you minus 1. Okay. Then let's continue with our notes. So we were here. So the critical value. So maybe I can number them like this to avoid confusion. Maybe go to D. Go to D. We say that rejecting the null hypothesis, rejecting the null hypothesis means that the regression coefficient being tested means that the regression coefficient being tested is significantly different from 0. So it's not 0 in a significant way. So that means it's either larger than 0 or smaller. So that the bit in brackets here will always be guided by the alternative hypothesis that you are trying to test. So either larger than 0 or less than 0, or we can add these, or is different. Let me see this. Or is different from 0. Because there are times when you're doing the two-tail test. So it's different from 0. Either larger than 0 or less than 0. Or we don't care whether it is large or small, but it's just different from 0. So let's have a practical example. So let's consider this example. This example is coming from the wages data. This is wages data, and we are going to fit multiple linear regression of the wages on the education and the tenure of service. So X1 and X2. So X1 here is the variable education, the number of years in education, and this is the tenure. Then our Y is the wages. It's wages. Then we have the number of observations is 526. So N is 526. And clearly, if you run the regression model like this using Excel, it is easy for you to see that K, what is K? The number of parameters being estimated is 3. We have estimated these 3 parameters, 1, 2, 3. So from there, you can be able to get the degrees of freedom. But you notice that when the degrees of freedom are so high, the T statistic is just equal to the normal, to the standard normal statistic. Okay. So I want to use this information. As you can see, we have the coefficient, the standard error, the calculated statistic, and then the p-values. Okay. So it's good for you to note that this T statistic here is the default. Statistic when we are testing the hypothesis H0 that beta j is equal to 0 versus H1 that beta j is different from 0. So that T statistic is only obtained that way, or it corresponds to this kind of hypothesis. So I want us to try this, use the above information to test the hypothesis. These are default hypotheses, so we use the information in the tables, but we have some special hypotheses, which I'll be explaining a little bit later, like Roman 2 and Roman 3, where we are not, sorry, this one should be equal to 1. This one should be equal to 1. So beta 1 is equal to 1. Or you can say that the null hypothesis, the alternative hypothesis will be beta 1 is less than 1. Okay, then we are testing about beta naught. We are saying it is equal to -2 versus H1 that beta naught is not equal to -2. Is not equal to -2. Okay, so let's solve the first one. Let's solve the first question. Then the other questions will be solved a little bit later. So solution, we are testing the hypothesis. We are testing the hypothesis given. So we are testing the hypothesis that we are testing the hypothesis that H naught, that beta 1 is equal to 0 versus H1, that H1 is different from 0, which is calling for a two-tailed test. So this calls for a two-tailed test. And because n is large, please note that because n is large, we use the standard normal distribution. We use the standard normal distribution. When n is large, when n is bigger than 30, you use the standard normal distribution to obtain your statistics here. So, and alpha is 5%. We're using alpha is 5%. So you can have, we're going to have our values here. And we know that when alpha is 5%, a two-tailed test will give us minus 1.96 plus 1.96. Okay, we have a question from Victoria. Yeah, so thanks for the correction. This is a typing error here. So this is a beta 1 is different from 1, it should be like that. Okay, and we're saying that if the sample is large, then the t distribution is approximately equal to the normal distribution. So we'll switch to the normal tables. We'll switch to the normal tables. So the critical values here will be obtained from the normal tables like that. Then from the output, our calculated statistic is t is from the table we're given the value of t is 0.569 no, sorry, not that. The value of the t statistic is given here 11.66. So is 11.66. And you want to make a decision now. So we say the calculated value of t or z in this case falls in the, so this is where it falls. This is 11.6. 11.6 should be deep in the rejection region, somewhere here, 11.6. 11.66. Huh? So falls in the rejection region. It falls in the rejection region. Thus, we reject the null hypothesis. That is H naught that B1, beta 1 is equal to 0 in favor of, we reject this statement here in favor of H1 that, sorry, this is what? Yeah, so this is a 0. That's a 0, sorry about that. Yeah, that's 0. So beta 1 is equal to 0 in favor of beta 1 is different from 0 at the 5% level of significance. So we reject the null hypothesis. So that means the regression coefficient beta naught, the regression coefficient beta naught, beta 1, the regression coefficient beta 1 is different from 0. Is different from 0. So that means that the variable corresponding to beta 1, which is x1, so variable x1 has a significant effect on y. So that means, so thus the variable x1, and x1 here we said is education. The variable, yeah, education, the number of years in education, education years is significant in estimating, predicting variable y, that is our wage. in predicting or estimating the wage. So basically, that's how you test hypothesis. So if you are doing, if you are performing a similar hypothesis, for beta naught and beta 2, will do the same thing. So this is significant. So this value here is significantly different from 0. Okay. Now, before we answer Roman 2 and 3, I want to mention what we call the general format of the null hypothesis. And that will help us now to answer Roman 1 and Roman 2. I mean Roman 2 and Roman 3. So the general null hypothesis. So the general null hypothesis. The general null hypothesis is defined like this. So you say H naught that beta j is equal to, this is how we denote it, beta j constant is equal to some hypothetical value. So generally, this is how we define null hypothesis. The one that we have been using, or the one that we've used up there, it was a special case of this. So beta j is equal to 0 is a special case. So if this is equal to 0, if this item is equal to 0, it's just a special case. But here you can put any value. You can put any value here. So this is analogous to, remember, in the context of hypothesis testing for the mean, you are having that mu is equal to some mu naught. Okay, where this can take any value, including 0. So 0, if this is equal to 0, then that's a special case of the general format. So, and the test statistic is given by, so we adjust the formula that we mentioned up there, we make it more general. So we say T beta j is equal to beta j hat minus that hypothetical value like that, divided by the standard error of, sorry about that, divided by the standard error of beta j. So the divisor does not change. The only thing that changes is this value here, because the formula that we have used up there, and that's the default formula that is used by Excel or most of the software, is that you assume that beta j naught is 0. But it can be something else, like you've seen in example, in our above example here, Roman 2 and 3. The value of beta j naught is not equal to 0. Okay, then we note that beta j naught is a hypothetical population parameter or constant. Hypothetical population parameter or constant. Okay, so now let's relook at this example. Now let's relook at so let's revisit above example. Now we're talking about Roman 2, where the question was, so please notice that if the value of the hypothetical constant is not 0, you will not use these values. You will not use the default values of t. We only use this one because we were testing the hypothesis that 1 is equal to 0, because we were doing that. If we had put something else, then these values of t should change. So let's look at Roman 2, that beta 1, that value is equal to 1. Then you see what happens there. So let's have H naught, that beta 1 is equal to 1, versus H1, that beta 1 is, what is the alternative hypothesis? That this guy here is, what did you say? Less than or greater than? Yeah, it's less than 1. Yeah, it's less than 1. So it's less than 1. is less than 1. So the alternative hypothesis is calling for a lower tail test. This is calling for a lower tail test. So let's say at alpha is 5%, you can use any other level of alpha, but if you're not given the level of alpha, use 5%. So we're talking about alpha is, so it means that we shall put our rejection region on one side like that. So this is the critical value here. So, and what is the critical value there? Remember, we are assuming the normal distribution because n is very large. So using the standard normal tables, we'll get that value. And then after that, we need to get the t calculated. And the t calculated will be given by this formula, where this is the value that is hypothetical, is the value that is captured in under H naught, okay? Which in our case is 1. In our case is 1. I think I've hidden it there. So in this case, we'll be having our beta 1 estimate, and our beta 1 estimate is gotten from the tables up there, from the output. From the output, we have our beta naught. Someone, if you have it, you can just mention it. Our beta naught estimate, sorry, a beta 1 estimate, which is 0.5691. So this is 0.5691 minus the hypothetical value, which is 1, divided by the standard error of beta 1. This will not change. So you will copy this one from the output, which is how much? What is the standard error from the output? The standard error
0.0488.
Yes, 0.0488. 0.0488. And you can simplify that and let me know what you get. So the calculated statistic is minus 8.83. So that's the value you want to place here and see whether it is in the rejection region or in the acceptance region. And clearly, your value is here, minus 8.83. Minus 8.83. So the calculated statistic, falls in the rejection region. Falls in the rejection region. Okay. So we conclude that. So we conclude that. So we reject the null hypothesis. So we reject the null hypothesis. We reject the null hypothesis. We reject H naught that beta 1 is equal to 1. We reject that in favor of. We reject that in favor of H1 that is less than 1, 5% level of significance, and so on and so forth. So you can use any value. You can use any value here, just like you've seen in as you will see in Roman number 3. In question number 3, you also have some other values. So I want you to try the last part on your own. Then you can share with me what you find out. I'll also be sharing notes on how to use p-values. Okay, p-values. In most of the computer output, you will notice that after the calculated statistic, we have a column here for p-values. In some places there is called significance. So for instance, in our case here, we had p-values. When you look at this output, there is this column here of p-values. So these p-values are also useful in hypothesis testing. But it's good for you to note that these p-values correspond to the default hypothesis statement. That is a two-tailed test where the hypothetical value is 0. So if you change the alternative hypothesis, then you need to calculate the p-values manually. You need to calculate the p-values manually. For your class, you may not want to know how to calculate those p-values. But in case you're interested, I can share you some notes I have in another class, in another unit that I'm teaching. You can learn how they are calculated. But for now, you will be using the p-values to test the default hypothesis. That is a two-tailed test where the hypothetical value, the value being tested is 0. Okay, so I want us to stop there for today. I don't know that we have any questions.